Hello.
Yes.
So I'm switching off my video because that is lagging.
Okay.
So yeah, guys. So today our topic is neural radiance field. So someone has heard of that, or someone may have worked on that or implemented that thing. So anybody who knows neural radiance field? Anybody here?
Ujjwal, I'm sorry, actually the participants are muted, so they cannot be talking. Like during the end of the session, I'll unmute them so that if they have any queries, they can ask. But right now they're all muted actually.
Okay. Fine. So let me introduce that neural radiance field. So I'm just sharing my screen. So is it visible?
Yeah, it is visible now.
Yeah. So yeah, we can see, yeah, neural radiance field is a very novel method of generating complex scenes, okay, through the novel views. So what is the means of that, and where we can use of those things? Okay. So suppose we are given some scenes. Okay, we are given a scene of suppose a building or a tree or a India Gate or whatever are traditional buildings and all. So some people as a visitors go there and take image from different angles, right? So suppose we have 30 images of India Gate. Okay, and we want to create a whole scene from all the angles, okay, so that we can in future we can just rotate it and see from any angle. So here comes the neural radiance field. Okay, so this problem can be solved using two ways. So one is that after seeing those 30 images, we can create a 3D model of the India Gate, the whole scene, and the background and whatever the lighting is there, everything should be recreated in a 3D by a software or by using the 3D artist, and they can do many things, and they can build a realistic model of that, and we can just look into that and rotate it everywhere and see that. And so that was the traditional idea. And the second thing that comes, the researchers were doing are doing actually now. This comes actually in 2020. So the neural radiance field can also generate those views all around all the angles of a scene. Okay, and how it is efficient than other methods, we will just go in deep of that after introducing that, and how it does actually. So it does by optimizing an underlying continuous volumetric scene. Okay, so here we can see this is the, sorry.
Yeah, yes, Ujjwal.
So this is the one function that we optimize during the neural radiance field. Okay, so I can just give one example of that, how we uh, overcome this problem and what is the problem here and how we are solving that. So see, suppose for our example, we have a building. So don't judge the drawing. Actually, hello Divya, are you on mute? I
Yeah,
think
sorry. Yeah.
some messages are coming. Yeah. Okay. So suppose this is India Gate, and some people are visiting and uh, maybe clicking their photo from here. So this is the camera. We can see some people may click photo from this angle. So just for example, we are taking multiple angle from which someone can click some photo in that building. See, so someone may see from here, someone may see from here, someone may see from here. So from this camera, only this view is created, okay, or this view is captured only. And from this camera, only this view is captured. And from this one, the corresponding view is captured. So given those some of the discrete images of that scene, how we can generate the whole scene, okay, so that we can see all around the angles. So using deep learning, if we go through some typical deep learning, what would first come in our mind is suppose we should have some data set of images and the corresponding objects in 3D, okay, maybe a maze or voxel grid or some point clouds, whatever the representation is there traditionally, we can use that. So the first deep learning typical approach can be like this is our X and this is our Y, and there are some images, images of house, maybe images of building, maybe it may be anything. So this may be a tree. This may be house. This may be any building like that. So suppose we are going to just map through a neural network or whatever the deep learning approach we can try here, and we can map from here to here. We are given the image, we can generate the whole scene, okay, in 3D, maybe a voxel, maybe a point cloud or meshes. So what is the issue in that deep learning approach is we would have a large set of data sets. Okay, we require a large set of data sets, multiple images of trees and their corresponding 3D objects, multiple objects of house, multiple images of buildings or whatever we want to build, and their corresponding 3D view or 3D objects in maze or voxel grid, whatever representation we can follow. So this is actually the fitting those data requires many time, and those approaches can also be not generalized to every view. Okay, so if we have trained on some of those data sets, it may not generalize to other data sets also. So so this was the one idea mapping as we use in the deep learning, and this is supervised type of learning. Okay, we are supervising these images and with their corresponding y values, means, their scenes. But how this neural radiance field is different from that approach is that we just need only images. Okay, so if we have images like 30 or 40 images of that India gate, and what we build here, we actually fit one function that is defined here, this continuous volumetric scene function, and that is represented by a fully connected fully connected neural network. Okay, so suppose we are having a neural network, simple neural network that is not having convolution layer itself. Okay, just a fully connected neural network. So giving input to that, these images, like 30 images we are giving 30 images to that, and it will give some values that will tell you that every angle this can be viewed. Okay, so just a neural network weights will do for you. So this is another way that we can approach this problem. Okay, so suppose we have these 30 images, so just we will just fit these images to that neural network, and this will tell you, yeah, this scene is India gate. Like some that the weights of the neural network just will tell you that this is India gate itself. So nothing, anything is not stored at maze or something. It's actually what is giving at weights is just representing the whole scene here. Okay, not a particular object, the whole scene. And scene may contain the background. Maybe if we are at the India gate, there may be many background, nice backgrounds. Okay, trees and everything, roads and everything, and buildings also. But when we are approaching with X and Y values, typical deep learning, so it will just generate the India gate for you. The whole scene is being generated, and that will be more heavy. Okay, so in here, this one neural network will represent that whole scene. So if we want to uh, fit another scene, so there would be another neural network. So here one neural network is corresponding to one scene. As we just save one OBJ file or any 3D file, mesh file, so we will just save or share this neural network weights, and at the client side itself, we can just render it down. Okay, so how flexible it is. And also we can say that this is more compact way. It's how it's compact is many informations are coming in between the layer itself. There is nothing extra things that we are saving, or there is nothing, everything, the whole content in the scene is coming just into this network. So not a different maze on different objects is created into the scene. The whole scene is there itself. So suppose how we are going to tackle this question, what will be the input to that neural network and what will be the output of neural network. So we should discuss that also. So input should be any location, any 3D location, and a viewing direction. Okay, in which direction we are seeing. Like here we are seeing in this direction, and some coordinates maybe we can take it here. And if we are seeing from here, so suppose we are seeing here, so there will be some coordinates x, y, z, and the direction itself. So suppose we are taking one point here, that is called x, and yeah, and we are seeing in this direction. So maybe we can denote the direction with two parameters. We say not this just a 1D direction. It's just this direction can be represented into theta and phi. So that is the 3D angle we can say here. Okay. So when we are seeing into from this direction, this point is x here. So this would go here as an input. Okay. This will go as input to the network, and what we will get as output is one is color at that point. What is the color of that point? This x, and what is the density there? Okay, density is like if we are seeing in some direction, if there is something, if there is something or there is some density. Density means we can say how much color is there or how much radiance is there, and if there is some radiance, what color it is. Okay, so this will act as output, and this is the input, and this x is nothing but just xy coordinates of that point, and this t is the direction. Direction is represented at theta and phi. Okay, so we can see here 5T input is going into this neural network, 5T, and we are getting this output, and that C is the color. So color can be RGB. Means at that point, what is the value of R, G, and B, and this one is the size, the 4D dimensional mix here. Okay. So here also you can see in this figure, this XYZ theta and phi is going into that feed forward neural network, and we are getting this RGB sigma as a output. Okay. So at the last means what we are going here and how it will be used. The, suppose we are saying we ask the neural network, hey neural network, you in your entirety, you represent this scene, and you are trained well, and if you are overfitted to that scene, I want to know at a particular location in the scene, viewed from a particular angle, what I'm going to see. Okay, so suppose at this point we query that neural network. The I want to know what we can see at this location uh, when viewed from this direction. So neural network will say, yeah, there is nothing because I could not see anything. Is here at point X there is nothing. Okay, but when we query at that point, suppose in between the scene, in between the object, there is something. Okay, so suppose at if we are seeing at X dash, so there is something, and maybe the we can see red color. So for every point, we can query the neural network what we can going to see in this at this location and at the direction. So that is the whole procedure. So how we are replicating the 3D scene into a neural network that can be queried at any point in seen from any direction, and that will tell you, yeah, this is you are going to see at that position if you are seeing from that direction. So how nice it is. We can just uh, take some overview from here. This is a nice and very compact representation of any 3D. So yeah, so this was just a kind of introduction and brief how it works and what is the neural network skills, and how it is efficient than the traditional deep learning approaches that we are using for creating scene or visualizing any scene to the users. So you can just take some uh, key insights from here. Okay, so now we can move to the other sections, how we do that. Okay, so for how we do that, we can just go into these 3 steps. So suppose we are having many pictures, we can see here itself. Yeah, suppose for a scene we have many pictures like pictures A, picture B, or whatever. Many pictures can be here, and we are marching rays to that. Okay, so suppose we can recreate the scene here. This was okay. So this was our scene, and suppose we have images. Images here, or maybe from many directions. So what we do here, we pass rays from every pixel of that image. Suppose we have pixels here, here, here. There may be many pixels. Okay, so just in an image, there may be many pixels. Okay, so like that. So we are passing rays from here to see what we are getting at each point of that ray. Not each point. We will use some sampling methods to sample some points on that ray. Suppose we have points here, 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 or maybe here. Okay, so we have some points on the ray that we are passing through each pixels of that image, and this is the first step. We are matching rays and sampling some points on that. Okay, and what is the second method? The second thing is that use point from a step one and their corresponding to the viewing direction, and give the input to the MLP to produce the set of colors and the density signal. Okay, so how we are going to do that? Suppose this is marching, and we got something here. Okay, so we can see a nice graph, kind of, just visualize. Suppose we are sigma, this is the position. Right. So we are traversing here, traversing, and we see something in the point, in the scene. So sigma will increase, and then again, if there is nothing, it will just go down like that. Okay. So when we are traversing through here, so through that point, we are not seeing anything. And when we just went here, we saw something. Here we saw something. It's any color or something, and density is also there. This is just empty space, so that's why we could not see anything. There is no any color. But neural network is predicting color for every points, but there is no density, so we will just remove it. As I saw, if there is something, is density is there, then we will calculate the colors there. Yeah, we will tell you, yeah, this is the density and the color. So this kind of approach we are going to follow. And the most interesting thing that we can take care here is when we have some kind of scene that is having some transparency inside that. Okay, so it will handle that transparency also. Okay, or maybe at this point we are seeing this is X and this is X dash. Okay, so at here we see a green color. Okay, and after going here we saw some blue color. Okay, so and in between there is nothing, or there may be any color, but the point that we are querying are having these colors. So when we are taking some transparent object, like when we are just take a glass kind of thing. Okay, having this layer is red, and this is blue maybe. Okay, so when a ray will trace it down from here, so it will give some red piece blue color here, and some with some lighting effect, and blue color here. So in that graph we can see that kind of. Okay. So we can realize that it can handle the transparency also. If there is multiple colors in between and there is nothing in there, so it will tell you, yeah, this can be handled here. So two things. One is the transparency, and lighting effect. It's maybe radius, and when we see from this direction, there is red and there is blue. So, and this is glass. Okay, so we can see reddish blue, is some sort of red, and some uh, radiance is coming from this layer also. So reddish blue. So here the lighting effect will be kind of a reddish blue kind of. Okay, and but the most of the color is red. So it will tell you that also lighting effect. What is the lighting effect at that point where we are querying, and if there is transparency in between. And the third step So yeah, we can discuss these three steps, how we actually implement this whole neural network and the whole pipeline, how we can implement. So first was the marching camera ray through the scene to sample 3D points. So this is the sampling. This is just for one pixel. So we can take many pixels from that. So suppose we have 64 into 64 pixels in an image. So there would be 64 into 64 rays we are passing through. Okay, and how many points we are taking. So those things can be defined, and sampling techniques can be modified in other versions of that nerve. And for this only images, we have this much of the rays. Okay, so this much of the pixels. So for this image, there would be another number of pixels. So for this image, maybe some images from here can have different number of pixels. So those much rays are passing through that, and we are getting some densities at some query point and the color. So after getting those densities and the color, the third thing is how we are going to uh, evaluate that process or optimize that process to get to get closer to that ground truth images. Okay, so here comes the volume rendering techniques. Okay, so what we will do, we will integrate all those points what we are getting at each point, the sigma and the color. So after integrating is after combining those things, collaborating those things into a single things, what we will get is for each pixel we will get some color. Okay, so that will be a kind of reconstructed image. Okay, so for every rays we are reconstructing one image. Okay, for every pixel we are giving some values what we are getting from passing those rays. Okay, so this was the ground truth images. From this pixel we are traversing the rays, and what we are finding here, we are just noting down at this pixel in that reconstructed image. Okay, so this is we can say I reconstructed, and this one is I. Okay, I and IR. So for all those images we will do the same thing. Okay, and at last what we will do, we will compare the images. Okay, how much different is that rendered image or the reconstructed image from the original image, through a mean squared error, a simple error that we can take it here, for example, like that. At point we are getting that kind of images, and this is the ground truth images, and we are just checking the loss here. Okay, so in this example we can see clearly. In here what we see, we can just like that, I minus IR, or maybe IR minus I. We are getting the model. So in this manner we will calculate the loss, and since this whole procedure is differentiable from the first step, like marking the rays, sampling the 3D points, and the getting the C and sigma value after giving the input to XY Z coordinates, and uh, the viewing direction, and the rendering these volumes that we are getting from this second step to a reconstructed image. The whole procedure is differentiable. So that's why we can use any gradient descent technique to optimize that whole procedure. Okay, so this is the key idea of this method. So if we are going to use any deep learning approach, we will just take care of if that method is defensible or not. If that is not, just tend towards the we have to make it differentiable somehow, and so that we can use a gradient descent technique to optimize the whole processor. So the same thing we are doing here. So one thing also, so when we see here, minimizing this error across multiple views encourage the network to create a coherent model. So we mostly see from the first images. So if we are taking multiple views, it encourages us to network predict a coherent model. This from every location, there may be a different kind of color or different views we can see, which different color we can see. Okay, some lighting effect can be different if we are seeing from different directions. Okay, suppose we have taken a bowl, and in there there is some water or something, and we are seeing from different direction, so lighting effect can be different on the top of that water. Okay, so this multiple view will tell the network to include those underlying scene content where at that particular location what could be some emitted radiance. Okay, so this was a kind of the things that we were going to implement, and there were many hints in there. This was just a simple implementation. Okay, this was just a simple implementation, and if we are going to implement it, there was some problems that we actually faced. Okay, so what we faced actually, some of in some of the images there was resolution effect. Okay, so that resolution was not very high. Somewhere we are losing the resolution. Okay, resolution means when we are going to capture very fine details, it was losing. Okay, with the basic implementation that we just described here. Okay, so for that we actually approach two techniques. The first is the positional encoding. So if yeah, in our just our session, there will be many guys who are familiar with that positional encodings. Okay, so in the transformer itself, we have seen many positional encodings. So that positional encoding is a bit of different, not that we are using here. So that positional encoding was telling you what is the position of relative words in terms of the other words. Okay, but in here it will tell you what would be the resolution here and here. Okay, in the images itself. So we can see here the basic implementation does not converge to the sufficiently high resolution representation and is inefficient in the required number of sample per camera rays. So that was the first issue, and it was solved using the positional encoding. And what it does, the positional encoding here, what it does is, suppose we have these 5D coordinates that we are giving as input to the neural network. Okay, so that was real numbers. Okay, those X, Y, Z, and what was that? Theta, and one was phi. Okay, so these were belonging to real numbers. Okay, so when we are giving to this neural network, so actually there is some behavior of neural network. It tends toward learning low frequency functions. Okay, it is not biased toward learning the high frequency functions. Okay, it is actually biased toward learning low frequency functions. So for that, when we just experimented, then we realized when we are just mapping it to higher frequency functions, uh, these xyz coordinates and the theta phi, when we are just mapping it to a, uh higher order of dimensions, so this fitting or the resolution issue that we were getting and the converging issue of that neural Radiance field was overcome. Okay, so for that we have used the positional encoding here so that we can represent higher frequency functions. Okay, so neural network was not able to do that, so we modified the input itself. Okay, we were just giving the input as a in a higher dimensions. Okay, so now this r is converted into r to the power 2l. Okay, so now this is converted into r to the power 2l. What is 2l? So this is l. L is the frequencies hierarchy function that we are going to use. I will just explain it briefly. What is that and how we are going to do that. Yeah, so here we can see after using this positional encoding, our input is modified. So our whole procedure that we were using, the f theta was made functions. Okay, that 5D coordinate function here that we have defined at the top itself. Yeah, this f theta. So f theta is not just this one. F theta is just modified at f theta dash, and f theta dash is f theta is modified as f theta dash into a gamma, and gamma is the positional encodings. Here we can see. So just reformulating the whole equations as this one. F theta is now f theta dash into gamma. So gamma is the positional encoding encoded here, and this one was the original neural network that we are calling. So one has to be learned and one is learned already. So this gamma does not need learning. Okay, that is just a mapping from lower dimensions to the higher dimensions. Okay, so it significantly improves the performance. So how it does, and I will just collectively tell you what was the other thing here. The second optimization was the hierarchical volume sampling. Okay, so when we are what we can say, yeah, when we have that much of higher dimensions points in between, sampling there using the dense sampling method is not very efficient method. Okay, so there were many points, there are many empty spaces, there are many what we can say, there is nothing in the scene. So those points are also being queried or also being sampled at that point. So this is not a very efficient method. So that's why we used hierarchical volume sampling. And also what it give advantage, it focuses us capturing the coarse details and the fine details at the same time. Okay, so where we should look to get some what is the affected area and what is the efficient area in the scene, whole scene. There may be a area in which there is nothing in the scene. There are some areas that are more attractive or are having more densities and the colors. So those areas should be more sampled instead of those empty spaces. Okay, so using those two method, coarse and the fine things, we are actually providing the network these informations. Yeah, just go through these course points and find something. So if this is the most probable area, we will give some fine sampling there. Okay, and that will capture the higher details. So that's how we overcome this whole problem. The problem of these high resolution things and the capturing the fine detail things. Okay, so how it does actually. So what it does, suppose we are taking one frequency functions like that. Okay, so one is with the lower frequency, maybe a sine function like that, and yeah, other thing can be that. Okay, like that. Yes. Or more higher one we can see like that. I'm just giving a brief idea about that, how we overcome that resolution problem, and the how we are tackling the problem of that inefficient sampling methods. Okay, so in here, when we are seeing some points, okay, this is positions and this is sigma, we can say. So when we are going from here to here, suppose this is one is point and this one is the point here. So in this one, in this frequency functions, we are getting value here and the here. So changes in that, you can see changes is very low. Okay, so these changes are very low. But if we just go here, somewhere here or here, this in every coordinate system, it's representing some of the points. Okay, in their respective coordinate systems. If we are taking any spaces, so these are the higher frequency functions that we are taking for. That was the L. So for the coordinate system, we are taking L is equal to 10. This like this function, we are taking 10 of these kind of frequency functions. And the direction one, we are taking 4 of these frequency functions. Okay, so that we can just take one point and map it into the higher dimensions. Okay, suppose from coming from here to here itself, in this coordinate system is giving so much changes, right? At this point, see from here to here, this is x and this is x dash. So from changing here to here, just x dash, there is no effect in this frequency functions. There may be not in here, but there is some here, but there is huge frequency changes here. So like that, we sample the points. First, we go for the coarse points. So this will represent the coarse things. Okay, these coarse changes is when we will move to very far, then we will see any changes. Okay, and this will declare some fine changes. If we just move uh, very small distance, changes will be high. Okay, so like that, we incorporate two networks here. We are not just learning one neural network. At the first, when we were defining, we are talking about in the basic implementation, we were talking about a single neural network that is just fitting into the scene, and that will tell you at each direction, at each point, what we are going to see. But while implementation, we saw some drawbacks, and then we incorporate these two methods, and the results we got is very enhanced. Okay, so we are taking two neural networks here and minimizing two losses here. And how we are doing that? So first we are taking NC locations, means NC number of core samples from a stratified sampling techniques. Okay, and then we are giving it to the neural network to evaluate on top of that on those course points. Okay, and after getting outputs from those course points, suppose from very far distance, suppose this is ray 1 and this is ray 2. So in this one, we are sampling course pointers, course points. Okay, so these are course points. So going into that race, suppose we are get nothing here, we are get nothing here, we are not getting anything here. Suppose we get something here, okay, at this point. So what should we do? We should query more points in here itself. Okay, like here, 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 and here. Okay, so this is the most effective area, or what we can say most attractive area we can see. So we should sample here so that this course point will tell you, the course network will tell you you should go in that affected area. Okay, and this fine corresponding fine network has many points. These all points are very fine, at very small distance. So after getting this idea from the course network, we will give the output to that fine network, and fine network will be evaluated on these course samples and these small points. Okay, these fine points. So the course network will be evaluated on just NC samples, but this uh, fine network will be evaluated on NC plus NF locations. Okay, so that we can get the course and the fine details at the same time. These are some equations that are being taken from the paper itself. So I think we don't have that much time so that we can discuss it in detail. Okay, because this is too much mathematics, and if we get some time in future, we can discuss about those things. But for the ideas, I think it's this much is very much to understand this now. And so yeah, so getting these two neural networks and optimizing those two things, how we are defining the loss here. Okay, so we are defining the loss just in a simple way, the uh, mean squared error for both the scores and the uh, what do we call it, just fine neural network. Okay, separately. So for all the rays, here we can see the losses here. Okay, so for all the rays, we are giving to all the pixels, we are just minimizing the coarse network and the fine network. So somehow we are taking the final details and everything from the fine network, but we are also optimizing the coarse network so that it can tell ki, yeah, this should be the whole area where we should look. And if that is optimized collectively with the fine neural network, so it would be more efficient way to tell everything. Okay, so just not look to the final details. Where you have to look finer, it will tell that while whole procedure. So for training, so what we are doing, just for learning, we can see at each optimization step, we are taking some batch of camera rays randomly sampled from set of all pixels in the data set. And then we are sampling some NC samples from the coarse network and NC plus NF samples from the fine networks. We are evaluating those both separately and just calculating the loss in a collective manner. So this will give us the RGB colors and the alpha value at that point. So these are some hyperparameters that are being used while training. We can check it. And going toward the results, we can see here how those scenes are being generated and some comparisons. Okay, so see here, SIP is there, and we can see this is the ground truth taken as an image. Is from any directions this image is taken. This one, and this one is generated by our NER. So this is kind of similar, and this is generated by LIFF method, and this was by SRN method, and this was from the other method. So this is the comparison here. So for getting the finer details, our nerve is looking good, very good, I think, in comparison with those other methods. We can see the finer details. We can compare with the ground truth. This one is the ground truth, and this one is the generated. So for some of the nice outputs that we can see here, see. So this is not a actually 3D scene or video. It's generated by rendering using the nerve. Okay, there are only some images of this phone, and the whole thing is looking like a whole scene is being captured, right? And look through that, means every scene details is there. There's no scene detail is being lost. If you see carefully, then also see here, the whole scene is captured very nicely. Also the color and everything, every details, fine details. You can see here birds and everything, leaves and everything. When any 3D artist will generate any models, and he will take renders from those angles, that model may not include these finer details. It can also be. It needs a very high precision 3D artist. So these are some examples. This is the whole 3D view that is being generated by this knob. Here you can see the lighting effect. See here lighting. This one is shadow is. This one is coming from light is coming from other direction. From here the light is coming from other direction. There is shadow in between. Also in here at the puff you can see different deep color is there, but from above it's little bit lighter color. So the whole lighting effect is there in that radiance field in generating a scene. See, for more finer details you can see each and every chain and every holes and everything is there in that model. Also this one. So these are some renderings outputs from getting from the nerves. So there is one thing that I just missed. So I will just explain it. When there is no positional encoding, so I just referenced one picture here that we can see. See, this is the complete model output. This positional encoding, hierarchical sampling, everything is incorporated in between that. So this is the final output. If there is no view dependence means if we are not giving any direction parameters into the network, so this is how it will look, the output one. And this one is with the no positional encoding. If positional encoding is not there, see how the chain and everything is coming here. Okay, so that's how the positional encoding and the direction things is helping our whole model to complete the finer and every details that we can capture. So where we can just have the application of that. So now it's an era of metaverse, okay, and AR VR things. So if you just want to put anything in that field in AR games or VR games, so what we do exactly is we create some 3D models or 3D scene or whatever we want to put in there. Okay, and we have to optimize it. Okay, we have to optimize it in such a way that it can be very less in weight and very efficient, so that everything can be rendered at runtime. And if we are giving finer details, the model would be very, very heavy, and it's a very actually difficult task for the 3D artist to tackle those problems and put everything into the AR or VR things. And if you have seen uh, in AR VR application, those fine details are missing in comparison with the 3D games that you play. In 3D games, there is everything is on your desktop, and those has more power to everything to be rendered. Okay, so at there it's kind of high processing things, but at edge devices like phones and the VR devices, those things has low processing units, so very efficient models and everything has to be used. So instead of those 3D scenes as maze or voxel or whatever representation we use, we can just use these neural radiance fields weights or neural networks itself, that is actually that we have implemented is only of 5 MB. Okay, of the scene, if we have one scene of that drum set, that was exactly having 10 GB of memory in 3D worlds. Okay, and but when we trained a neural network, in this neural radiance field, its whole scene is captured into 5 MB weights of the neural network. Even it's less than that image captured for those. So mostly now images are like 4 MB, 5 MB or something. So that's how effective this neural radiance field, and how it will come into the existence after 1 or 2 years. And that is actually an open area for the research. The one limitation we can say here is it takes 1 or 2 days to build in learning, okay, on a single P100 GPU memory. So that is one limitation. So, but that was in the 2020. Okay, now there are many versions of that neural radiance field has come, like instant nerve by the NVIDIA, faster nerve, and everything. Those are very fast and they render at they learn in a very good pace, so that we can use somewhere. And experimentally, we have not gone for all type of scenes, and and also the control is lesser in this neural radiance field. Okay, so these are some of the minor limitations, but I think there is huge potential for this field or this research that we can use. And also, the Google is actually going to use that neural radiance field for his next Google Map things. Okay, so everything should be rendered at real time in 3D using that field. So big clap for that. So I think this is it that I had to discuss in this neural radiance field sessions. And any feedback from your side would be welcome. So yeah, we can start.
Okay, so I think Punita wants to ask a query. Punita, ma'am, please unmute and ask.
What Divya? Sorry, I could not get.